last speaker for today is Wushi Goldring, and we'll talk about irregular automorphic Galois representations.
Thank you. So, like the previous talk, I'd like to, I'm going to fix my number field to be Q. So I'd like to look at the group, Galois group of Q bar over Q. And I'm interested in understanding representations of this group into GLN of QL bar. And the starting point is, as was discussed, that such things, some such things arise from automorphic representations. So let G be a connected reductive group over Q. Let pi be a cuspidal automorphic representation of the adelic points of G. Then we have a decomposition of pi as an Archimedean component and a finite part. So this is a representation of the real points, and this is a representation of the finite adelic points. And then a key notion is, so let chi infinity be the infinitesimal character of pi infinity, then chi infinity is regular if it's not orthogonal to any root. Pi infinity is regular if chi infinity is, and pi is regular if pi infinity is. So we have this notion of regularity. And on the other hand, we have the notion of being algebraic. So pi is algebraic if chi infinity is integral up to half sum of positive roots. So there's a slightly technical subtlety here. Okay, so we have these two conditions. And then, so the conjecture, which is part of the Langlands program, is if pi is algebraic, then there exists an integer n such that for all primes L, there exists a Galois representation RL of pi from the Galois group of Q to GLN of QL bar. And I'm not going to go into what this n is because I don't want to talk about functoriality. And similarly, I'm not going to put any L group. OK, so we have this conjecture which doesn't make any reference to regularity. But what I want to stress is that the difficulty of this conjecture is the key thing is the structure of the Archimedean component pi infinity. And so there's been a lot of work on this conjecture in the regular case. And so one theorem that was referred to in the last talk due to Harris, Lan, Taylor, Thorne, is that if G is GLN, or let's say if G is GLM and pi is regular algebraic, then the conjecture holds with m equals n. Okay, so we have very strong results in the regular case. And what I'd like to focus on for the rest of this talk is the irregular case. So the simplest irregular case is when pi infinity is a holomorphic limit of discrete series. So unfortunately, I won't be able to define exactly what this means, but if you are familiar with holomorphic discrete series, this is as close as you can get to a holomorphic, this is as close as you can be to a holomorphic discrete series without actually being one. And what I can tell you is geometrically, pi infinity holomorphic limit of discrete series, this implies that one can realize the finite part of pi in the H0 coherent cohomology of some Shimura variety with coefficients in an automorphic vector bundle. So studying holomorphic limits of discrete series is closely related to understanding global sections of Shimura varieties, of vector bundles on Shimura varieties. And so what is known in this case, so the first result is due to Deline and Serre, and this says that if G is GL2 and pi infinity is holomorphic limit of discrete series, this implies that the conjecture holds. So maybe theorem 1. Theorem 2, due to Taylor, says that if G is GSP4 and pi infinity is a holomorphic limit of discrete series, then the conjecture holds. And let me remark that in this case of Deline-Serre, this is the same thing as talking about weight 1 modular forms. And in this case, this includes but covers more than talking about weight 2, rank 2, weight 2 Ziegel modular forms. And the third theorem, which is due to myself and joint work of myself and Marc Hubert-Nicole, is if G is a unitary group, and pi infinity is a holomorphic limit of discrete series, then the conjecture holds at least for all but finitely many primes. Okay. L. So I proved this for a density 1 set of primes L, and now we have, I proved it for the split ones, and now we have extended it to the inert ones. Okay. How much time do I have left? Okay. So this is what I've done in the past, and now let me finish by saying what I plan to work on. So the next level of difficulty so the simplest case we said was when pi infinity is a holomorphic limit of discrete series. The next case is when pi infinity is a non-holomorphic, non-degenerate limit of discrete series. And the reason I say that this is the next case is over there we had a geometric condition in the holomorphic case. So pi infinity, a non-holomorphic, non-degenerate limit of discrete series. This means that the finite part of pi embeds into hk of a Shimura variety with coefficients in some vector bundle. And now k is strictly greater than 0 and strictly less than the top degree. So now you're dealing with cohomology classes on the Shimura variety, which seems to be much more complicated. And so the problem that I hope to work on here is to construct RL of pi for such pi infinity. And let me just say that so far, aside from functoriality constructions, which I can explain, aside from functoriality constructions, no known RL of pi with pi infinity not regular and not holomorphic limit of discrete series. Okay, thank you.